Hey guys, the objective of this video is to look at a drained example, and the way we do that is we first find the change in total stress, which is the change in effective stress, and because the sample is drained, there's no excess pore water pressures, which means that this relationship is true. We're going to find them in the X, Y, and Z direction. We're then going to find the strains in the X, Y, and Z direction, and then we can eventually find the volumetric strain. So I've got the same example we've done in the other videos. It's the exact same cube specimen where we've got 100 kPa on all faces, and then they're changed to mu values. We have an E effective of 5 MPa and a V dash of 0.2. So as always, we're first going to find the change in stress, and we can just jump straight to the effective stress because the change in total stress from here to here is the same as the change in effective stress because it is fully drained, which means that there's no excess pore water pressure. So we spoke about this in the previous video, that we said that the total stress is equal to the change in effective stress plus the change in pore water pressure, but because it's drained, so because we're looking at a drained case, that does not exist, and therefore we just have that relationship there. So the change in of X dash, we've gone from 100 to 80, so this is minus 20. The change in Y dash would be gone from 100 to 110, so we've increased by 10. And the change in Z dash, we've gone from 100 to 120, so we've increased by 20. So now it's very easy for us to find our strains. We know that the strain in the X direction for a drained example is the effective X, the change of stress in the effective X, minus V dash outside of change of Y plus change of Z dash. So this is all effective, and this is all on top of E dash. We could then find this value. This would be minus 20 minus 0.2, which is V dash, outside of change in Y dash, which is 10, plus change in Z dash, which is 20, all over E dash, which is 5 MPa. Keeping in mind we have to change that to kPa, because all our values are in kPa. If we were to calculate this, we would get an answer of minus 0.0052. We could then find the change in the Y direction, the strain in the Y direction. So it would be 10 minus 0.2 outside of minus 20 plus 20 all over 5,000. And we would get an answer of 0.002. We could then find the strain in the Z direction, and this would be 20 minus 0.2 outside of minus 20 plus 10 all over 5,000, and this answer would be 0.0044. So that was very simple. All I've done to find this, E dash and V dash aren't changing for each case. The only thing that's changing is that for EX, this is change in X. For EY, this is change in Y. For EZ, this is change in Z. And the other values are put in the brackets. So for EY, that would be EX. So for EY, this would be change in Y. So change in X and change in Z, and this would be change in Y. So we've found all these values. That's all the strains. So it's very simple. The drained case is much easier than the undrained case. We can now find the volumetric strain. So EV is equal to just the components. So this is now the 3D volumetric strain, and these are just the components X, Y, and Z. So we would just add them up. So it would be minus 0.052. So minus 0.0052 plus 0.002 plus 0.0044. And we'd get an answer of 0.0012. Now we can also find the volumetric strain through this method if you wanted to. So we found it this way. We could also find it this way. The volumetric strain is equal to 3 outside of 1 minus 2 V dash outside of sigma M dash. That's the mean stress over E dash. So we first have to find the mean stress. And we know the mean stress is just 1/3 of all the components. So minus 20, 10, and 20. So minus 20 plus 10 plus 20. This would give us an answer of 10 on 3. We would then use that value to find EV, which would be 3 outside of 1 minus 2. V dash is 0.2. 10 on 3 is sigma m dash over the E dash, which is 5,000, and if we work that out, we would get 0.0012, which is the same value we got using this method. So we could find the volumetric strain just adding it all up, or we can find it through this formula and get 0.012. Anyway guys, hope that helps.